Have you ever wanted a remote that can control all of your devices? Smart TVs, old infrared TVs, and Rokus? Well, I have, and you can actually just buy one, but it'd be funner to make one, so let's do it. First, to start to any project, we need a computer to actually run the remote. Not this kind of computer, but a microcontroller, which is basically just a small computer. That leaves us with an ESP32. It has Bluetooth and Wi-Fi support. It has a little high power draw, but that'll be okay. I had an ESP32 S3 Dev Kit C laying around, so we'll go with this. The first step of this project is a way to interface with the user. I'll use this 240 by 240 LCD display that uses an ST7789 driver. It uses an SPI interface, so I can connect all the data lines and I could hook up the VCC to 3.3 volts. After wiring it up, we can install this Adafruit library for the display and run its test example. The display runs and looks good. Also, sorry if this video looks like it was filmed on a baby monitor. That's because I'm filming with my one camera iPhone. So now to actually make the display useful, we need to create some menu navigation. I created this simple list navigation thingy. It'll do just fine. We can then just add a few buttons to the main menu for our various features. Our first feature to implement is infrared. I bought this IR emitter and IR receiver so we can handle the IR data. So for the receiving end, we can use this IR Arduino library, which will let us read the IR codes and send them. For the emitter, we can just take those raw codes we received and relay it back through the emitter. Since I didn't have an IR TV, I just bought one of those cheap LED lights with one of those infrared color changing controllers. We can test out reading these IR values from the controller and then try to emit them back through our LED. As you can see, it works. This works and all, but when we turn off the device, the RAM is cleared and these IR codes will not save. For this, we can use the Arduino Preferences library, which will store our data in flash memory along with our program. Next, we need some sort of input, as we have no way to control the display or the infrared. We could just add a bunch of buttons to the GPIO pins on the ESP32, but given that we're going to have 12 buttons, that's 12 GPIO pins used just for buttons, and we haven't even added all the features. So the only other funner option I could think of is to make our own PCB. Now, we could have just done this for the whole project, and this would come back to haunt me later. The first step in this process is we have to make a schematic. The chip we're going to be using is an MCP 23017 GPIO expander. Basically, we can add more GPIO pins to our ESP32 with the expander and interact with the MCP through an I2C interface. We just add our buttons and some debouncing capacitors, and that's pretty much it. To actually create the physical layout, we need to assign footprints to the schematic of the physical layout of components like the IC and the switches. I placed the buttons in a sort of remote layout and drew traces to the MCP's pins. Then I just put the I2C data lines and power to a header at the top, and that should be good. Unfortunately, I don't own a $100,000 PCB fabrication machine, so we will need to get this manufactured somewhere else. I'm going to go with JLC PCB because supposedly they are the cheapest. I upload my PCB files and the parts I want assembled, and then a few weeks later, it comes from China and it arrives. Now to actually make it useful, we can use this Adafruit MCP 23017 library to interface it with our menu. Then for the infrared control, we just send whichever saved code depending on the button. Okay, so now we've got one feature done. Let's focus on Roku now. Unlike other smart TVs, Roku Stick does not allow Bluetooth connection to other peripherals. They do, however, have something called ECP, which stands for External Control Protocol, which allows us to send the Roku device key presses. All ECP is a REST API, meaning we can just create HTTP requests on our local network to our Roku to control it. First though, we need a way to connect our ESP32 to Wi-Fi. We can use Arduino's Wi-Fi library to handle these connections. We simply just type in SSID and password and that's it. But how can we type a password with only 12 random buttons? We can't. But since our project is already going to be using Bluetooth, we can add Bluetooth text input. Basically, we just create a text input service on our ESP32's Bluetooth to accept text input from other devices like, say, our phone. Anyways, going back to the Roku control, now that we have a Wi-Fi connection, we can now create an HTTP post request to our Roku. But wait, To make an HTTP request to our Roku, we need its IP address. Luckily, something called SSDP, or Simple Service Discovery Protocol, exists, which will scan our network and find the Roku's IP. We simply just copy the HTTP body from the documentation and get our IP. Now, since it's a simple REST API, we can just send a post request corresponding to the button we want pressed with an empty HTTP body. But what about smart TVs like Apple TV or Fire TV? Since those devices are even smarter, they allow Bluetooth connections, not just to remotes, but several Bluetooth devices, even game controllers and stuff. To connect our remote to those smart TVs in a language they understand, we can use HID, or Human Interface Device. We all use these every day. It's how our keyboards, our mice interact with our computers at application level. At usb.org, you can find HID codes for a bunch of stuff if you ever want to control a pinball device or even a tank machine simulator. Here we find codes for menu navigation and power control, which is what we want. The Arduino Bluetooth library includes a Bluetooth HID device class, which we can use for our remote. When we want to send a key, we just grab its HID code, and to release it, we send all zeros. Now that we have all our features implemented, this is really coming together. But we can't keep this all on a breadboard, and we need some way to make it portable. We need a battery. The components for the battery circuit, we will use a 1000 milliamp 3.7 volt LiPo battery, then this cheap 3.7 volt LiPo battery charger with a voltage regulator, and then just this Adafruit battery monitor to get the battery's voltage for simple battery level indication. Adafruit also provides a library for this. What we can do is create a loop that will read the voltage and then calculate rough quarter percents for battery charge. These aren't the most accurate because temperature and other factors contribute to a battery's discharge rate, but looking at the datasheet for this battery, we can compare values to this discharge rate graph and try to match up values as best as possible. This obviously isn't the best or efficient solution, but whatever. With pretty much all features implemented, we can finally move on to making this thing a little more portable and actually usable. To create this case, I took this remote model off of Sketchfab, and thank you for the model. Then yes, we paste it into Tinkercad. I don't care what anyone says, Tinkercad is easy, and I hate 3D modeling anyways. I gather up 3D models for all our components and then just find a good layout for all the components and then just start on the enclosure. After I modeled everything, we are ready to 3D print it out. Try to do one of those cool 3D print time lapses, but my bed also moves, so it just looks stupid. After the print is finished, I can put in these brass threaded inserts for mounting points for all the components. It's time to solder everything. Soldering this was near impossible. There was just way too many wires in a small place, especially for a portable device like this, and not even near as annoying as stuffing it into the enclosure. And here's the result. I am pretty disappointed at the outcome. You can see these edges on the screen could be cleaned up. The plain buttons look terrible, and there's a pretty significant bulge. This is mostly due to my dumbass not just building a PCB for everything, but it works. Let's do a reflection. I think the code was decent and implemented alright. I could have probably improved the battery circuit as the voltage from the monitor was a little spotty, and I would like a more accurate battery percentage. For the case, I'm pretty disappointed about the build quality, and if I could go back and redo some things, that would be fun. Fortunately, school is starting and I have to lock in, so maybe a V2 sometime later. But in the end, I learned a ton and had fun, so that just means my next project will be even better. Thank you guys for watching, and please leave any comments on suggestions or something I may have missed, and have a good day.